Okay, let's have a look at May 2009 C2 Circles question. It is question 8 of that paper. Okay. I've already drawn part of the picture which I'll be using later in part C. So the circle that's drawn there is used in part C, so ignore that for the moment. Okay. So, part A tells you we've got a circle which is C1, which has an equation x squared plus y squared minus 6x plus 2y minus 15 equals 0. And we simply have to work out what the coordinates of the centre A is and what the radius of that circle is. So, usual standard calculation then. So, x squared, put the x's next, then the y squared, then the y, take the 15 to the other side. Complete the square. It'll be x minus 3 squared, compensate, take away 9. Plus y plus 1 in a bracket squared, compensate, take away 1. Equals 15. Okay, reorder it. X minus 3 in a bracket squared, plus y plus 1 in a bracket squared. Take the minus 9 minus 1 to the other side, become positives. You end up with positive 25. So you can see straight away that the centre of this first circle is 3 minus 1, using those brackets to help me. Minus 3, 3, plus 1, minus 1, and the radius is the square root of 25. I'm actually going to plot that now on this picture. This picture isn't really accurate, but it's not bad. The one that's already drawn, as I said, is part C, so forget about that. I'm actually going to plot that in this picture. 3 minus 1. 3 minus 1, well, the centre, quite awkward to plot, but I'll do my best. It's A, there it is, and the radius is 5, so I would be tempted to get a compass out and draw this. In the last example I did, which I think was January 2009 C2, I didn't even do a sketch at all, basically because it wasn't necessary. But having spent just 30 seconds prior to starting this video looking through the question, it became abundantly clear to me to be able to do part C successfully, I really did need to have a sketch to be able to explain what was going on. And so sometimes you need a sketch and sometimes you don't. You have to think on your feet. If in doubt, do a sketch. Do it accurately, use a compass, it may help you. Okay, so centre 3 minus 1, I've plotted it, there it is, and radius is 5. Well, I'm not going to do this with a compass, but basically if the radius is 5, 3 to 8, from 3 it'll go to minus 2. It's a bit cluttered here, but I'll try and get the picture decent, and then we go minus 1 to plus 4, and minus 1 to minus 6. So this looks something like that. So that is C1. Okay, so I've done C1, there it is. I'll refer to that circle when I come on to part C. Okay. On to part C a little bit later. Let's now do part B. Part B says we've got a point P with coordinates 7, 2, which lies on C1 apparently. Well, if I look at this, 7 is there, 2 is there, yep, thank heavens for that. We've got a point P there. And point P has a tangent drawn. Okay, so we've got a tangent at point P. And it basically says find the equation of the tangent to C1 at P. Find the equation of that tangent at that point, the P. Well, the tangent is a straight line. You want to find the equation of a straight line, which from C1 work uses coordinate geometry. You need to know two things. You need to know a point on the line. Well, I know that. The point P lies on the line, and the point P had coordinates 7, 2. So I know a point on the line, and you need to know the gradient of the line. Well, I do not know the gradient of that tangent. Right, at this point here we make use of some circle work which you did way back in year 11. You should know, if I join this up now, like so, that is the radius of the small circle C1. You should know that any radius is perpendicular to a tangent. How does that help us? Well, I know the coordinates of A because I've found them. I know the coordinates of P because I'm told them. That means I am able to work out the gradient of that line A to P. If I know the gradient of the line A to P, and I know that the tangent is perpendicular to that radius line AP, then I can work out from coordinate geometry the gradient of the tangent AP simply by flipping it upside down and changing the sign, which is a coordinate geometry technique. If I know the gradient of the tangent, I can use the point P to go with it, and I can work out the equation of the tangent. So that's what I'm going to do. So here we go, part B. I'm first of all going to look at the line A to P, which is that radius I've drawn, and I'm going to work out its gradient, which I'll call M. Okay, well, there's a lot going on there, so I'm not going to put any more notation in the picture. I'm going to call P x2, y2. I'm going to call A x1, y1. So I'm going to simply do y2 minus y1 over x2 minus x1 as the formula for the gradient of a line joining 2 points, which is coordinate geometry work. So the gradient of AP will be y2 is the 2 value of the point P. Take away y1. Now y1 is the y value of point A, which, if you remember the centre point was 3 minus 1. So x1, y1 are 3 minus 1. So I've got 2 take away minus 1. So that's plus 1. You get a double negative. All over x2. x2 is the x coordinate of P, which is 7. Take away, and then x1 is 3 from point A. So you get the gradient of the line AP, that radius there, is 3 over 4, which is a positive quantity, which makes sense because it is sloping in a positive sense. So therefore, I can now write down immediately that the gradient of the tangent must be equal to minus 4/3. Because it's perpendicular to the radius from Year 11 circle theorem work, you can simply flip those upside down and change the sign. Because the test of perpendicular lines is if you multiply the two gradients together, you get an answer of minus 1. And you need to write down that little test, as we did for the coordinate geometry questions. So I now know the gradient of the tangent. I now know the point P72 on the tangent, so therefore the equation of the tangent I can now work out. So the equation of the tangent can be found by using y minus, well, I called that x2, y2 a minute ago, so it's going to be y minus y2 equals the gradient, well, if I call that m1, x minus x2. Okay, so y minus y2, it's going to be y minus y2. Well, what is y2? y2 is the y coordinate of the point P, which is 2, equals m1. m1 is the gradient of the tangent, which I've worked out here, minus 4/3. Not the 3/4, it's the minus 4/3 for the tangent. Minus 4/3. And then x minus x2. Well, x2 is the x coordinate of P, which is 7. There you go. Get rid of the 3, so treble everything. 3y minus 6 equals, and then expand out the bracket as well, minus 4x plus 28. So you get 3y plus 4x, take that over, you're going to get minus 34 is equal to 0. And there you go, that's the equation of the tangent at point P. Okay, and that was worth 4 more marks. Okay, then quickly moving on to part C, and this is where I'll make use of this circle I'd already drawn. So part C, get rid of all of this. Okay, part C now introduces a second circle which they call C2 with centre B, which 11, 14, with a radius of 8, which I've plotted reasonably accurately in the picture. And as you can see, we've got a situation where we've got two circles in the question now, And it's one of these situations where the two circles do not overlap or touch at all. They are totally separate from each other. Okay? Now what we've got here, this question is quite a difficult one to get your head around. What we've got is that there's a point Q which lies on C1. So Q is somewhere on C1. And there's another point R which lies on C2. So R lies somewhere on C2. It could be anywhere. Now a bit of common sense comes in next. It says, find the shortest possible length of the line QR. The shortest possible length. Right, well, the shortest possible length will come about. Let me get a colour, see if we can make a bit of sense out of this. The shortest length, right, let me join up in red the two centre points of the circle. Okay? On this circle here lies the point Q. Now obviously if it's down here, okay, you're not going to have the distance from Q to R to be as short as possible. The distance Q to R, R's on this circle, Q's on this circle, the distance Q to R will be short as possible when the R goes down to that point there and the Q goes round to that point there. So from the picture I can mark in that R must have gone to there and Q must be there. That is the situation where you've got the 2 points Q and R as close as possible. When they are on a direct line from the centre to the centre. That distance there is the closest possible approach point of Q and R. Okay, so what does this mean? Well, it means, this is the logic I'm going to use now. I know that the radius of the small circle from there to there was 5. I know the radius of the big circle from there to there was 8. Okay? So what I'm going to do now is work out the distance from A to B or B to A. The distance between the two centre points. Hopefully it'll be more than 13 because 8 and 5 make 13. And whatever it is more than 13 by will be that gap there. And that gap there will therefore be, ignore the loud chiming in the background, that gap there will be the shortest distance apart QR that it is possible to have. So, I'm going to work out the distance A to B, which is the distance between the two centre points. This is coordinate geometry C1 work. Okay, so here we go. A to B. Distance, this is part C I'm doing now, equals the square root of, okay, if I call A was x1, y1, if I call B x3, y3, so it's going to be x3 minus x1 squared plus y3 minus y1 squared. Working out the distance between the two, thank heavens for that, between the two centre points. Okay, so it's equal to the square root of x3, it's 11. Take away x1, x1 was 3, this one up here, 3, this is the centre A, okay, 3, inner bracket squared, plus y3, that's 14, take away y1, that was minus 1, so be careful, you get 14 take away minus 1, so that's plus 1, inner bracket squared. So you're going to get the square root of 11 take 3 is 8 squared, plus 15 squared. So you get the square root of 64 plus 225, which is the square root of 289, which, if you get a calculator out and check this, nicely works out to be 17. So I know the distance between the two centre points is 17. Okay, so if the radius of the big one is 8 and the radius of the small one is 5, 8 and 5 make 13, that obviously means that the gap in between from Q to R, if it's going to be as short as possible, it must look like that distance from Q to R. So therefore the shortest Q to R distance that is absolutely possible is simply the 17, the gap between the two, Take away the 8, take away the 5. And if you do that, the shortest distance, Q to R, is a distance of 4. And it's got to be when they're in that position. Obviously, if I put R over there, or Q down here, the distance from Q to R will be much greater. That is the distance which is when it's at its shortest, and its value is 4. Okay, for that one there, I would definitely recommend you do a diagram. If you try doing that without a diagram, I think most people would get a little bit unstuck, become a little bit unstuck. Okay, that's the end of the question.